Bismillah ar-Rahman ar-Rahim. Assalamu alaikum and good morning. We are Group 3. We are here to talk about atomic absorption spectroscopy. Our group is composed from me, Muhammad Abdul Munim, and Noor Yuni, and also Tiar. So let's start.
Atomic absorption spectroscopy, or AAS, is an analytical technique used to measure the concentration of metal elements in a sample. AAS works based on a very simple idea. Every metal atom absorbs light at its own unique wavelength. By measuring how much light is absorbed, we can determine how much of that metal is present. AAS is widely used to detect metals such as calcium, magnesium, iron, zinc, copper, titanium, chromium, and many others. It is known for being accurate, selective, and relatively easy to operate. In biomaterial, AAS is extremely useful for analyzing metal ion release from implants, detecting trace metal in scaffold, and monitoring biomaterial degradation, especially for metal-based implants. So, in simple terms, AAS tells us how much metal is inside a sample using the concept of light absorption by atoms. The working principle of AAS can be explained in a few clear steps. First is atomization. The sample, usually in liquid form, is introduced into a flame or a graphite furnace. The high temperature converts the sample into free atoms in the gas phase. This step is important because only free atoms can absorb light effectively. Next is the light source. A hollow cathode lamp is used, and this lamp is designed for a specific metals. For example, if we want to measure zinc, we use a zinc lamp. The lamp emits light at a wavelength that matches the energy absorbed by that specific metal's atoms. Then comes the absorption process. As the light passes through the cloud of free atoms, those atoms absorb part of the light. Each element absorbs at its own unique wavelength, which is why AAS is very selective. After that, the detector measures the absorbed light. If more light is absorbed, it means there are more atoms in the sample. If less light is absorbed, it means the concentration is lower. Finally, quantification is done. The absorbance values are compared to a calibration curve made from standard solution. This allows the instrument to calculate the exact concentration of the metal in the sample. So overall, the working principle of AAS is based on this relationship. More atoms to more absorbent light to high metal concentration. This makes AAS a powerful and reliable technique for analyzing metals in biomaterials.
Okay, and the key component of AAS, we have like five main components. First one, we have the light source. This is very crucial because it's not just a generic light source. If we are testing for copper, for example, we must plug in a copper lamp. It's emit the exact specific wavelength of light that only copper atoms can absorb. Second, we have the atomizer. The beam travel all the way to atomizer. Before it gets there, our liquid sample is sprayed into a fine mist by the sample introduction system inside the atomizer. Extreme heat, usually from a flame, destroys the sample matrix and turns it into cloud of free floating atoms. If our target element is present in that cloud, its atom will steal or absorb some of the light passing through. After the flame, the light enters the monochromator. The burning flame creates a lot of extra light and noise. The monochromator acts like a very strict filter, blocking all that background noise and only letting the single specific wavelength we care about pass through. Finally, the remaining light hits the detector. The computer compare how much light left the lamp versus how much actually arrived at the detector. The simple rule is the less light that arrive at the end, the higher the concentration of the metal in the sample. Okay, as we can see from the image over here, the the lamp, which is the hollow cathode lamp, is the light source over here, and the light travels from this source to the computer. We see it's passing through the atomizer first, and the sample introduction system is connected to it. Then it's entered the monochromator filter, and after that hit the detector, and the information sent to the computer. Okay, so we know how it's work, but why is AAS the industry favorite for so many labs? First and foremost is specificity, because AAS uses light source capable of interact with only one specific element. It's incredibly reliable. It's ignore everything else in the sample. Uh, it's like having a metal detector that ignore iron and steel and only beeps when it finds gold. Second, the sensitivity. In many industry, we aren't looking for a chunk of metal. We are looking for invisible contamination. AAS can detect metals at a part per million, or even part per billion. To put that in perspective, that's like finding a single drop of dye in an Olympic-sized swimming pool. Third, the costs, obviously. While there are machines like ICP-MS that can measure 50 elements at once, they are incredibly expensive to run. If you only need to check the purity of your copper prototype or test water for arsenic, AAS is the most economic choice without sacrificing accuracy. Finally, because it's reliable. It is the regulatory standard. If you are submitting a report for legal environmental complaints or food safety, AS often the method the government requires you to use.
Slide, I'm highlighting 6 key applications of biomaterials using AAS. First, AAS measures metal ion release from implants, which helps assess their safety inside the body. Second, it analyzes calcium and phosphate in bone materials to evaluate bone regeneration performance. Third, AAS tracks metal-based nanoparticles such as iron oxide used in drug delivery. Fourth, detecting trace metals in hydrogels to ensure they are safe and biocompatible. Fifth, studying magnesium implant degradation by measuring released Mj plus 2 ions. Finally, monitoring metal levels in the patient's blood after implantation. Overall, these examples show how analytical techniques support safe and effective biomaterials.